Welcome. This screencast is going to look at the first part of Chapter 5 in Section 1, and we're going to take a look at the big questions that Rutherford's work left unanswered for the chemists that followed him. So Rutherford and Thomson came up with these subatomic particles, figured out we have electrons, protons, and neutrons, and Rutherford's gold foil experiment showed us that the nucleus has got the protons and neutrons just packed really, really tight into a really small space. But then the electrons are in this huge cloud around this nucleus, which is mostly empty space. So Bohr thought maybe the electrons moved in these predictable orbits, and it was very much like the solar system. And then Rutherford and others said, no, they move more random than that. But yet it's not totally random. It's not a total free-for-all. So the big questions were, how are the electrons arranged around the atom? And then why aren't the electrons pulled into the positive nucleus, or why don't they just escape totally from the atom if it's mostly empty space? And then finally, what accounts for the difference in chemical behavior among atoms? Some atoms, like the noble gases, are almost totally unreactive, like helium. Then you have things like hydrogen, which are extremely explosive and flammable. So what's the difference? What makes some things highly reactive, others practically non-reactive, and then a bunch of elements somewhere in between? So in the early 1900s, chemists found that certain elements, especially metals, emit visible light when heated in a flame. And I'm not kidding. If you go home and if you have like an iron nail or a piece of copper and you heat it in a flame, you will see it gives off a characteristic color. That's what we now call atomic emission spectra. And we're actually going to look at this in class with some flame tests, and it's really cool. And in fact, this is what goes on in fireworks. Fireworks, you're seeing the different colors being emitted by metals when they're being heated as the firework explodes. So scientists found that this and all of an element's chemical behavior is connected to how the electrons are arranged in the atom or in the cloud. So here's the confusing part. Because it gives off light, and light's a form of electromagnetic radiation, which is a form of energy, we have to do some physics work in Chapter 5. So electromagnetic radiation is a form of energy that exhibits wave-like behavior as it travels through space. I know that sounds kind of complicated, but if you look at the list, this is pretty much all the energy you can think of except for sound waves. So when you think of waves like visible light, the white light we see, or the pretty colors when it goes through a prism, or I'm sure you've heard of ultraviolet light, black lights you see, infrared, TV, radio waves, X-rays, microwaves, gamma waves, those are all types of electromagnetic radiation. So one thing you should realize about electromagnetic radiation is they all travel at the same speed. We happen to call it the speed of light, or c, because that's the type of electromagnetic radiation we can see. So before scientists realized there was a whole bunch of different waves that all traveled at this speed, they discovered it was light. And in fact, when they realized it was a constant speed, that's where they came up with the c for it. So that speed is 3 times 10 to the 8th meters per second, which is really fast. That's why when you flip the light on, it's like instantly the light is on, the switch is on, and the light is reaching your eyes. It is fast. What makes electromagnetic waves different is this thing called wavelength, frequency, and amplitude. So we're going to take a look at what those three characteristics how they differentiate or make electromagnetic waves different from each other. So here's a graphic. I've got a couple graphics here for you of what's called the electromagnetic spectrum. So radio waves are the longer waves with low energy, and X-rays and gamma rays, cosmic rays, those are up at the high energy end and have very short wavelengths. And then kind of the in-between things are the infrared and ultraviolet, which we can't quite see, and then the visible light that we can see. And you notice that along with this visible light, they show it breaking off here, that visible light, white light, really has good old Roy G. Biv, red, orange, yellow, green, blue, and violet. And you'll notice red is on the long wavelength, low energy side, whereas violet is on the higher energy, shorter wavelength side. So here's another graphic, and you might want to just pause and take a look at this. But this just gives you an idea of just how long and short these different waves are. Radio waves are longer than buildings, which is why they're able to move around buildings and still reach your receiver, your radio. Whereas when we get up to gamma rays, they are much, much smaller, like the size of atoms and the nuclei of atoms. Here's a graphic to show you what we mean by frequency and wavelength. So wavelength is said to be measured from crest to crest, which is the top of the wave. You can also measure it from trough to trough, which would be the bottom, and you'll get the same length. But the idea is you have to measure between two identical points on the wave. So you can see that wave A up above, the red wave, has got a much longer wavelength than B down below. But what's different is if you were to sit right here over in the right-hand corner and watch waves go by, if you counted for a minute red waves and purple waves going by, you would have a lot more purple waves go by than red waves, and that is frequency. And that's why we measure frequency in per seconds, which Hertz conveniently named after himself, so you can just call it a Hertz instead. Or oftentimes it's abbreviated S with the -1, meaning per second, because remember, a negative exponent means it's 1 over whatever that number is. So how do we use this? Well, we're going to take a look at the relationship between wavelength and frequency. If you didn't notice on the previous slide, wavelength and frequency have an inverse relationship. When one gets bigger, the other gets smaller. The other thing physicists found out is that wavelength times frequency always equals the speed of light. So in order for this to work, since speed of light is given in meters per second, that means your wavelength has to be in meters and your frequency has to be in hertz or per seconds. Also, you should realize that when frequency increases, energy increases. So I've got a couple examples here for you to work through to finish up this video. My first example says a helium neon laser emits light with a wavelength of 633 nm. nm is nanometers. What is the frequency of this light? So a couple of hints for you. We only have one equation to use. C equals wavelength, that's the upside down looking Y or lambda, times V, which is frequency. So we only have that one equation, but the wavelength has to be in meters, so this needs to be changed. Frequency has to be in hertz. Well, that's okay, because that's what I'm trying to find is frequency. C is always the same value or number, which is 3.00 times 10 to the 8th meters per second. So I would encourage you to pause and try and do this before you look at the next screen where I go through the solution. So using those hints, we use the equation C equals lambda times V. But the wavelength is 633 nanometers. So the first thing I did is I set up a conversion factor with the unit I want, meters, over the unit I have, nanometers. That means when I take 633 nanometers times this conversion factor, my nanometers cancel out, and I'm going to be left with meters. And I chose to use the conversion factor from off the helping hand that says 10 to the -9th meters are in 1 nanometer. And I'm just going to leave this as 633 times 10 to the -9th nanometer, or 633 times 10 to the -9th meters. Technically, scientific notation, I should have 6.33, but when I do that, then I get all confused. Is this 10 to the -11th, or is it 10 to the -7th? I don't have to think about it if I just wait till my final answer. So then when I plug into C equals lambda times V, I have 3 times 10 to the 8th equals 633 times 10 to the -9th meters times V. So since I want to solve for V, I'm going to divide both sides by 633 times 10 to the -9th, and make sure you put brackets around it so that your calculator knows that's all one number. Do the same thing over here, 633 times 10 to the -9th, and I came up with a frequency of 4.7 times 10 to the 14th. I use the label of S-1. You could also label it Hertz or just HZ, or you could actually put the slash and then second below. Here's another try it. An FM radio station broadcasts at a frequency of 98.5 megahertz. What's the wavelength? So to get you started, remember, we only have the one equation to use. We know C has to be 3 times 10 to the 8th meters per second. I'm trying to find wavelength, but before I can plug V in, I need this to be in hertz. So I'm going to have to take my 98.5 megahertz and set up a conversion factor to get that to hertz. So I'd encourage you to pause this and see if you could solve this on your own, and then check out my solution on the next slide. So I went ahead and took the 98.5 megahertz, and I set it up with hertz over megahertz. So the megahertz cancel, I'm left with hertz. And just like I did with the nanometers, I go ahead and leave my answer as 98.5 times 10 to the 6th because I'm not done calculating yet. So when I plug in 3 times 10 to the 8th equal to lambda times 98.5 times 10 to the 6th, again, I want the lambda alone, so I'm going to divide each side by the 98.5 times 10 to the 6th. And making sure I use my brackets, I will come up with a wavelength of 3.045 meters.